Hello, class. This is a lesson on 3.1 for Precalculus, Exponential, and Logistic Modeling. By the end of this lesson, you should be able to use exponential growth, decay, and regression to model real-life problems. What I'm going to start with is just showing you how to get a constant percentage rate. This goes along with the exponential population model that you took notes on prior to coming to class. So here's how it works. Suppose that a population is changing at a constant percentage rate R. Where R is the percent rate of change expressed in a decimal form. Then the population is going to follow the pattern shown below here. So here's what you can consider. Time in years, 0, that means we're talking the initial population. So after 0 amount of time, P sub 0, that represents the population that you start with. Well, after 1 year, you can get the new population by taking the old population, P sub 0, and adding to it whatever the percentage rate is that the population is growing by, times the initial population. So if the population increased by 5%, you would take the initial population times 0.05 and add that to the initial population to get the population after 1 year. Well, if you factored out the initial population from this, you would have the initial population times 1 plus R. Well, after a second year, you could take the population you had the year before times that same 1 plus R. So what that's saying is whatever the previous population was, multiply by that plus the rate it increases by to get your population after 2 years. So another way to look at this is if you multiply by 1 plus R, you're going to keep last year's population, and you're going to add to it the amount of people that your rate has predicted. Notice it's the same formula, just 1 plus R is raised to the second power since we're at year number 2. And then same thing is true in the third year. You take the second year's total times that same 1 plus R to get your new population. And after following that pattern, quite quickly you see after T years, you take the initial population times 1 plus the rate raised to whatever year you're looking at. And that brings us to our exponential population model, which is what we just mentioned. If the population is changing at a constant percentage rate R each year, then it can be modeled in this way, where P sub 0 is the initial population, R is a decimal that represents the rate in which it's changing, and T is time in years. Now, in the previous example, I talked about the increase, but it doesn't always have to be an increase. This first example that I'll show you, we're looking at finding if it's a growth or decay. Well, so the question is, tell whether the population model P of T equals 786,543 times 1.021 raised to the T is an exponential growth function or an exponential decay function, and find the constant percent rate of growth. So what we're going to look at here is the value right here. We could rewrite this as P of T equals 786 5, that's a 5, 43 times 1 plus 0.021 raised to the t. Well, when you're adding to the 1, or when you have that number bigger than 1, you know that's exponential growth. What's the rate of growth? Well, this decimal here tells us 0.021. That would be a growth rate of 2.1%. In this next example, finding an exponential function, I want you to determine the exponential function with an initial value of 10, increasing at a rate of 5% per year. Why don't you pause this and try to do that right now? Well, you probably found that since your initial value is 10 and the rate is 5%, you would take 10 times 1 plus 0.05 raised to the t. Which one simplified? You would just combine that to 1.05. This next example, modeling bacteria growth. Suppose a culture of 200 bacteria is put into a petri dish and the culture doubles every hour. Predict when the number of bacteria will be 350,000. And then I start you off here with a little information. Why don't you go ahead and pause, see what you can do with this problem. So if the culture starts with 200 bacteria, we're going to let our t value, instead of represent years, represent hours in this case. So when t is 0, you have 200. So after 1 hour, we'd have 400. After 2 hours, we'd have 800. So without too much effort, you'd come up with this exponential function. So the question is, when will the number of bacteria be 350,000? So you could represent 350,000 for p of t and solve for t, as shown here. You could do that using your calculator if you want to. If you plug y equals 350,000 in and y equals 200 times 2 to the t, let's see if that's what I have in here right now. So that's what I have in my calculator right now. If I just go to the graph on a normal window, this is what I would see. Well, you know that you're looking at y to be 350,000. So you would want to change your window to represent something more along those lines. So I want y to be 350,000. So I'll just go 349,900 to 350,100. So I'm surrounding that area there, and we can let that be 25. You could have a lot of different windows here. I just want to make sure I see what I want to see. Now I don't know how many hours it'll take, so I know it's going to be greater than 0. And let's just throw in 20 hours and see what happens. If I look at my graph now, I'm hoping to see an intersection of a horizontal line and another line. Well, it looks like I've found an intersection there. I don't get a real good look at what the graph looks like, but I have the intersection on my graph. That's the whole point. Now if I could use my calc feature. Number 5 says the intersect. First curve, yes, yes, guess. I don't remember what my range was, but I'm gonna, since 10 is on there right now, I'm just gonna guess 10.2. What's the answer? The intersection is at 10.77, so it wasn't quite right, but pretty close. What does that 10.77 represent? Well, that's going to be my t value. That's the time. Remember, the t in this case was hours, so 10.77 hours after you start. That gives us our answer of when the bacteria would be at 350,000. Pretty amazing stuff. Think about what that means. Think about how fast that grows. Yeah, I know. It's amazing. All right. So here's another example. What I'd like you to do is you're going to model the U.S. population using an exponential regression model. What you're going to do here is you're going to take and put this data into your calculator. I want you to put the years over here. I want you to put these years under list 1, and I want 1890 to represent 0, 1900 to represent 1, and so on. And then this is under list 2, your population in millions. So you just write these exactly as is. Put that in your calculator now, pause, and proceed. Now you all should have that in your calculator. I want you to now make the scatter plot, show that, and I want you to come up with, look under your regression equations and figure out which one you should use to get the model that we need for an exponential regression equation. And then I want you to figure out, according to that model, what you expect the population to be in the year 2000. Once you're done with that, compare with each other, and I want you to pause now, and when you're done working on this, play this video some more and you'll see the answer. So now what you should have done was you should have entered the data into your calculator. As I mentioned, so the year 2000 would be represented by x equals 11. Create a scatter plot. So you put the data into your calculator. Set it in an appropriate window. Well, actually, you could just use your zoom stat function. That's the best way to do it. So I actually wouldn't even worry about this. I just use zoom stat. Make your scatter plot. And then what you should have found was there's an exponential regression function on your calculator. If you use that, you should have gotten A to be 66.9928 and B to be 1.1488885, niner in there. Okay. So if you graph that, remember what the question was. You're trying to find, we better go back up and look. Predict the population for the year 2000. So that's when x is 11. You could plug x equals 11 in, or since you already have your graph, you plug this into your calculator. You can just use your calc value option, so then you don't have to plug all that information again. Just use the calc value option and look at the value when x is 11, what the population would be. What this means is the year 2000 would be represented by, or the predicted population would be 311.66 million people. The actual population was, sorry for scrolling up and down so much, the actual population was approximately 281 million. So this estimation was approximately 31 million over what it actually ended up being. This next note is going to help us, or we're going to be able to use our logistic function. Excuse me. We're going to be able to use our logistic function to estimate different populations. Maximum sustainable population. Exponential growth is unrestricted, but population growth often is not. For many populations, the growth begins exponentially, but eventually slows and approaches a limit to growth called the maximum sustainable population. So we're going to use that in this example. So this is an example of modeling a rumor. I'm sure there's no rumors that go around here at Hudson High School. A high school has 1,500 students. 5 students start a rumor, which spreads logistically so that S of t equals 1,500 divided by 1 plus 29 times e to the negative 0.9t. Models the number of students who have heard the rumor by the end of t days, where t equals 0 is the day the rumor begins to spread. Okay, so make sure you get that written down, mainly that S of t data. And then the first question is, how many students have heard the rumor by the end of day 0? This kind of helps you get an idea of how this equation is set up. Well, by the end of day 0, that's when t equals 0. So basically, to get that answer, you're going to take 1,500 divided by 1 plus 29 times e to the negative 0.9 times 0. Well, e to the 0 is going to be 1, so it's 1,500 divided by 30. So that was the easy problem. Now, how long does it take for 1,000 students to hear the rumor? How are you going to do this? Well, the S of t represents how many students have heard the rumor. So you just simply plug in 1,000 for S of t. And then solve. You could use your grapher again. Why don't you pause the video at this time and solve that. So now, once you do that, you would find that t is approximately 4.5, so 1,000 students have heard the rumor halfway through the 5th day. That's the last example for these notes. Your assignment is on the board.